Right now, at this exact moment, trillions upon trillions of atoms inside your body are doing something absolutely wild. They're rearranging themselves, breaking apart, snapping back together, releasing tiny bursts of energy that keep you warm, keep you alive, keep you watching this video. And here's the kicker: you have no idea it's happening. You can't feel it. You can't see it, but it's there every single second in a dance, so precise and so violent that if you could zoom in and watch just one of these atomic events unfold in real time, you'd never look at fire the same way again. Because when something burns, when you strike that match, or light that candle, or watch that forest go up in flames, what you're actually witnessing isn't just heat and light. You're re-watching atoms tear themselves apart and rebuild in ways that release the same fundamental energy that powers stars. And today, we're going deep. We're going inside the atom itself to see exactly what happens when matter decides to burn. If you're ready to see the invisible world that has been hiding in plain sight your entire life, hit that subscribe button right now, because Physics Decoded is about to show you reality at a level most people never get to see. Let's go. Okay, so first things first, we need to talk about what an atom actually is, because most of us learned this in school and promptly forgot half of it. An atom is the smallest unit of matter that still behaves like the element it represents. It's got a nucleus in the center, packed tight with protons and neutrons. And around that nucleus, you've got electrons zipping around in what we call orbitals, or electron clouds. Now, here's where it gets interesting. Those electrons aren't just randomly floating around doing whatever they want. They're arranged in very specific energy levels, like invisible shelves around the nucleus. And the electrons on the outermost shelf, the ones farthest from the nucleus, those are the ones that actually do all the work when something burns. These outermost electrons are called valence electrons, and they're basically the social butterflies of the atomic world. They're the ones that interact with other atoms, form bonds, break bonds, and ultimately decide whether a chemical reaction is going to happen or not. When you light a match, you're not just heating up some wood and chemicals. You're giving energy to those valence electrons, enough energy to break free from their current bonds and go looking for new partners. And when they find those new partners, when they snap into new arrangements, that's when the magic happens. That's when energy gets released. That's when you get fire. But let's slow down for a second, because I want you to really understand what a chemical bond is. Imagine two atoms sitting next to each other. Each one has its own cloud of electrons buzzing around. Now, if the conditions are right, those electron clouds start to overlap. The electrons from one atom start interacting with the nucleus of the other atom, and vice versa. It's like they're sharing their electrons, holding hands in the atomic world. This sharing creates a bond, a connection that holds the two atoms together. And that bond has energy stored in it, kind of like a stretched rubber band. As long as the bond exists, that energy is locked up, waiting. Now here's the thing. Not all bonds are created equal. Some bonds are strong, meaning they hold a lot of energy and are hard to break. Other bonds are weak, easier to snap apart. And when something burns, what you're really doing is breaking weak bonds and forming strong bonds. Let me say that again because it is crucial. Burning is the process of breaking weak chemical bonds and replacing them with stronger chemical bonds. And the difference in energy between those weak bonds and those strong bonds, that difference gets released as heat and light. That's fire. Let's take wood as an example, because we've all seen wood burn. Wood is mostly made of cellulose, which is a big molecule built from carbon, hydrogen, and oxygen atoms, all bonded together in specific patterns. Those bonds are relatively weak. They're stable enough to keep the wood solid at room temperature, but they're not the strongest bonds carbon, hydrogen, and oxygen can form. Not even close. So when you heat up that wood, when you add energy from a match or a lighter, you're giving those atoms enough energy to break free from their current bonds. The heat makes the atoms vibrate faster and faster until those weak bonds snap. And once those bonds break, the atoms are free agents. The carbon atoms, the hydrogen atoms, the oxygen atoms, they're all looking for new partners. And guess what's all around them? Oxygen, tons of it. About 21% of the air we breathe is oxygen gas, which is just pairs of oxygen atoms bonded together. And oxygen is hungry. Oxygen loves to form bonds with other elements, especially carbon and hydrogen. So when those carbon and hydrogen atoms break free from the wood, they immediately start bonding with oxygen from the air. Carbon grabs oxygen and forms carbon dioxide. Hydrogen grabs oxygen and forms water vapor. And here's the key. The bonds in carbon dioxide and water vapor are way stronger than the bonds that were in the wood. Way stronger. So when those new bonds form, they release a ton of energy. That energy comes out as heat, which keeps the reaction going, breaking more bonds in the wood, freeing more carbon and hydrogen, which grab more oxygen, which releases more energy, and the whole thing becomes a self-sustaining cycle. That's combustion. That's fire. But let's zoom in even closer, because I want you to see what's happening at the atomic level during this process. Picture a single carbon atom that was part of a cellulose molecule in the wood. It's bonded to hydrogen atoms and other carbon atoms, sitting there in a relatively stable arrangement. Then heat comes in. That heat is really just kinetic energy, energy of motion. It makes all the atoms in the wood start vibrating more and more violently. The bonds start stretching and flexing, and at some critical point, one of those bonds breaks. The carbon atom is free. Now, floating nearby is an oxygen molecule, two oxygen atoms bonded together. That oxygen molecule is also vibrating, moving around in the air. Eventually, through random motion and probability, that free carbon atom collides with the oxygen molecule. But it's not just bounce off. The carbon atom's valence electrons and the oxygen atom's valence electrons start interacting. They start overlapping, sharing space. And because carbon and oxygen have just the right number of electrons, just the right energy levels, they can form a very stable bond. In fact, carbon loves oxygen so much that one carbon atom will grab two oxygen atoms, forming CO2, carbon dioxide. When that bond forms, when those electrons settle into their new arrangement, they drop to a lower energy state. And that extra energy they had before, it gets released. It has to go somewhere, and it comes out as a photon of light, and as kinetic energy, heat. That single reaction, that one carbon atom bonding with two oxygen atoms, releases a tiny, tiny amount of energy. But in a burning piece of wood, this is happening to billions upon billions upon billions of atoms every single second. All those tiny energy releases add up to the roaring fire you see. And this is where it gets absolutely mind-blowing. The light you see from a fire, those dancing yellow and orange flames, that's not just heat making things glow. That's actual photons being released as electrons drop from higher energy states to lower energy states. When a carbon atom bonds with oxygen, the electrons in that new CO2 molecule settle into their lowest, most stable configuration. As they drop down, they release energy in the form of light. Different reactions release different wavelengths of light, which is why flames have different colors. A wood fire burns yellow and orange because of the specific wavelengths released by carbon and hydrogen reacting with oxygen. A gas stove burns blue because the methane in natural gas releases different wavelengths. But it's all the same fundamental process. Electrons changing energy levels and releasing photons. Now, I know what some of you are thinking. If burning releases energy, where was that energy before? Great question. That energy was stored in the chemical bonds of the wood. When the wood originally formed, when the tree was growing, it was doing photosynthesis. It was taking carbon dioxide from the air and water from the ground and using sunlight to build glucose and cellulose. That process required energy, energy from the sun. That solar energy got stored in the chemical bonds of the cellulose. And when you burn the wood, you're basically releasing that stored sunlight. You're undoing photosynthesis. Fire is ancient sunlight coming back out. Let me give you another way to think about this. Imagine you're pushing a boulder up a hill. That takes energy, right? Once the boulder is at the top of the hill, it has potential energy stored in its position. If you let it go, it rolls back down, and that potential energy converts to kinetic energy, the energy of motion. Chemical bonds work the same way. Breaking a bond is like pushing the boulder uphill. It takes energy. Forming a bond is like the boulder rolling downhill. It releases energy. When you burn wood, you're using a little bit of energy to break the weak bonds. The boulder starts moving, and then the atoms form much stronger bonds. The boulder rolls way down the hill, and you get a big release of energy. But here's something even crazier. This process, this rearrangement of atoms and release of energy, it's not unique to burning. It's happening all the time, everywhere, in ways you'd never expect. When you digest food, your body is breaking bonds in the molecules you ate and forming new bonds, releasing energy that powers your cells. When a car engine runs, it's burning gasoline, breaking weak bonds in hydrocarbons and forming strong bonds with oxygen, releasing energy that moves the pistons. When dynamite explodes, it's the same thing, just way faster and more violent. all of chemistry, all of life, all of technology. It all comes down to atoms breaking and forming bonds, electrons rearranging themselves, and energy being released or absorbed. And the really wild part, the atoms themselves don't change. That carbon atom that was in the wood then became part of carbon dioxide. It's still carbon. It still has 6 protons, 6 neutrons, and 6 electrons. It's the same atom it was a billion years ago, and the same atom it will be a billion years from now. The only thing that changes is how it's bonded to other atoms. The universe is just endlessly shuffling the same deck of atomic cards, rearranging them in different combinations, and that's what creates everything you see around you. So let's talk about activation energy, because this is a key concept. If burning releases so much energy, why doesn't everything just spontaneously combust all the time? Why does wood sit there not burning until you add heat from a match? The answer is activation energy. Even though forming strong bonds with oxygen releases more energy than breaking the weak bonds in wood, you still need an initial input of energy to get the reaction started. It's like that boulder at the top of the hill. Yeah, it'll release energy when it rolls down, but you have to push it up there first. That initial energy, the match or lighter, it heats up a small area of the wood enough to break some of those weak bonds and start the reaction. Once it starts, the energy released from the new bonds forming is enough to break more bonds nearby, and the reaction becomes self-sustaining. But without that initial push, without that activation energy, the atoms just sit there in their weak bonds, stable enough for the moment. This is why you can store wood and gasoline and all sorts of flammable materials safely. They're not going to burn on their own. They need that initial spark, that activation energy. Different materials have different activation energies. Paper has a lower activation energy than wood, which is why paper catches fire more easily. Steel has a really high activation energy, which is why it doesn't burn under normal conditions, even though iron and oxygen can form bonds and release energy. You'd need to heat steel up to extreme temperatures to get it to burn. But here's a fun fact. Steel wool, which has a huge surface area, can actually burn if you light it with a flame or a battery. Same atoms, same chemistry, but the tiny strands heat up fast enough to reach activation energy. Now, let's address something that confuses a lot of people. When something burns, where does the matter go? You start with a log of wood, you burn it, and you end up with a little pile of ash. Did matter get destroyed? Nope. Matter never gets destroyed in a chemical reaction. It just changes form. That wood was mostly carbon, hydrogen, and oxygen. When it burned, the carbon became carbon dioxide gas, the hydrogen became water vapor, also a gas, and a tiny amount of minerals in the wood became ash. If you could capture all the gases released during the burning and weigh them along with the ash, the total mass would be exactly the same as the original log, plus all the oxygen from the air that reacted with it. That's the law of conservation of mass. Atoms don't disappear. They just rearrange. Here's another thing that blows my mind. The speed of these reactions. When you light a match, the flame spreads across the match head in a fraction of a second. In that time, billions of molecules are breaking apart and recoupling, releasing photons and heat, all in a coordinated cascade. And it's not random chaos. There are patterns, structures. The flame has layers. The hottest part of a candle flame is actually not the bright yellow part you see. It's a thin, almost invisible blue layer near the base of the flame. That's where the initial reaction with oxygen is happening. The yellow part higher up is soot particles, tiny bits of carbon that haven't fully reacted yet, getting hot enough to glow. They're giving off blackbody radiation, which is light emitted just from being hot. Eventually, those soot particles either burn up completely or escape as smoke. And speaking of smoke, that's just unburned particles and gases. In a perfect combustion reaction, you'd only get carbon dioxide and water vapor, nothing else. But in reality, combustion is messy. Not everything burns completely. You get carbon monoxide, soot, and all sorts of other compounds. That's why smoke is dangerous. It's full of partially reacted chemicals, some of which are toxic. Let's go even deeper. What about the electrons themselves? I said earlier that they're rearranging, but what does that actually mean? Electrons exist in specific orbitals around the nucleus, regions of space where they're likely to be found. These orbitals have specific shapes and energy levels. When two atoms form a bond, their orbitals overlap and merge, creating molecular orbitals that belong to both atoms. The electrons occupy these molecular orbitals, and their energy determines how strong the bond is. When you break a bond, you re-giving the electrons enough energy to escape from that molecular orbital and move to a higher energy state, usually a free state, where they're associated with just one atom again. When a new bond forms, the electrons drop into a new, lower energy molecular orbital, and that drop in energy is what releases heat and light. It's literally electrons falling to a more stable state, like a ball rolling downhill, and that energy has to go somewhere. And here's something that'll really bake your brain. Those electrons, they don't have definite positions. They exist as probability clouds. You can't say an electron is exactly here at this exact time. You can only say it's probably somewhere in this region. When bonds form and break, those probability clouds shift and change shape. The electron could be anywhere within its orbital, but when you measure it, when it interacts with something, it collapses into a specific position for that instant. Quantum mechanics is weird, and it's operating at the most fundamental level of chemistry, but we don't need to get lost in the quantum weeds to appreciate what's happening. The main point is this: burning is a chemical reaction where weak bonds break and strong bonds form, and the energy difference gets released as heat and light. And it all happens because of the behavior of electrons, the outermost parts of atoms, interacting with each other in precise, predictable ways. Now, here's a question. Can you burn things without oxygen? And the answer is yes, kind of. Oxygen is just a really good oxidizer, meaning it loves to grab electrons and form strong bonds. But there are other oxidizers: chlorine, fluorine, even nitrogen under the right conditions. If you put something flammable in an atmosphere of pure chlorine and ignite it, it'll burn, forming chlorides instead of oxides. The same fundamental process is happening: breaking weak bonds, forming strong bonds, releasing energy. Oxygen is just the most common oxidizer because it's everywhere in our atmosphere. There are even reactions that release energy without any oxidizer at all. When you mix certain chemicals, they react and release heat just from rearranging into more stable configurations. That's an exothermic reaction, and it's the same idea. The products are more stable than the reactants, so energy gets released. But what we usually call burning, combustion, specifically involves reacting with oxygen or another oxidizer and producing heat and light. Alright, let's bring this back to the big picture. Every time you see a fire, whether it's a campfire, a candle, a gas stove, or a wildfire, you're watching the same atomic ballet. Electrons are being shared and swapped, bonds are breaking and forming, energy is being released, and all of it is governed by the fundamental laws of physics and chemistry, the same laws that govern everything in the universe. There's no magic. It's just atoms doing what atoms do, following the rules, rearranging into lower energy states whenever they can. And this is what I love about physics and chemistry. Once you understand the rules, you start seeing them everywhere. You realize that the fire in your fireplace is the same basic process as the fire inside a star, just on a different scale. You see that the rust forming on old metal is the same bonding of iron and oxygen, just happening slowly instead of explosively. You understand that your body is a chemistry lab, running millions of reactions every second, all based on the same principles. So next time you light a match, I want you to pause for a second. Look at that flame. Really look at it. You're not just seeing light and heat. You're seeing atoms from the match head breaking apart, grabbing oxygen from the air, forming carbon dioxide and water vapor, releasing photons that traveled from the flame to your eye at the speed of light. You're seeing chemistry in action, the fundamental forces that build and break everything in the universe. And you're seeing energy that was stored in those chemical bonds, energy that originally came from the sun, being released back into the world. That's what actually happens inside an atom when something burns. It's not magic. It's not some vague hand-wavy explanation. It's electrons rearranging, bonds breaking and forming, energy being released, all governed by precise, beautiful laws of nature. And once you see it, you can't unsee it. Before we wrap up, I want to hear from you. Drop a comment below and tell me what's something you see every day that you want to understand at the atomic level. Cooking, rusting, batteries. Let me know, because we're going to keep digging deeper into the invisible world that makes everything work. And if this video changed the way you see fire, do me a favor and share it with someone who'd appreciate it. Send it to a friend, post it on social media, help spread the knowledge. Physics Decoded is all about taking the complex and making it clear, showing you the hidden mechanisms behind everyday phenomena. If you want more of this, subscribe and hit that notification bell so you don't miss the next deep dive. We've got so much more to explore, from the quantum world to the cosmic scale, and I can't wait to take you along for the ride. Thanks for watching, and I'll see you in the next one.